go back to, if we finish, let's say, early 4:30 or so, we can, what I like to, I'll be here till 5:30, 6 o'clock, and so I'd love to visit with some of you. And we can also go back to the inverter section to run some of the demonstrations which we skipped yesterday. Right, so let me get started with.
One quick question.
Pardon me? Yes.
Yesterday we discussed about the BLDC controllers. Today we didn't cover much on the sensorless BLDC controller. Actually, today when I covered about the sensorless speed controller over here, can you give me the brief discussion?
Yeah, I think in sensorless BLDC, okay, the application of sensorless BLDC is quite limited. It's limited mainly in very low-end applications. Okay, we have, if you are any application which is user critical does not really use sensorless BLDC. That is at least my view. Maybe people from Emerson can confirm it, as what your views are in that respect. And I think the reason is that, and normally it's a beautiful application when you are running blowers, you're running low-cost applications. It is not a good application when you're running high-end systems, right? So sensorless is
How exactly we determine the computation period means what we should do? In the sensor, we can have a feedback from the all sensors. In the sensorless,
well, there are two schemes, I believe, which are implemented. One is you're sensing the back EMF voltage in the BFDC. Okay, so what you can do is, and we draw it here. So you can, if you have a motor, and let's say I have, if I just draw a three-phase winding like this, right? Now I can have a resistor network which basically can imitate and I can sense essentially voltages across these resistors at, well, the issue always is starting. How do you estimate starting of a BLDC motor, right, without Hall sensors? If you don't have Hall sensors, how do you estimate where your motor is? You know, whether it's in, if you have, let's say, 6 segments, you know, 6 sectors, which sector are you in the motor, right? So this is a well-known technique, which is I believe patented by ST Microelectronics, and they offer it as a solution with their software, with their application notes, with their as a software, also implemented software, executed software when you use their microcontroller. Okay, so this is one way essentially you can estimate the rotor speed. Now you can. Now the other part is you can also, but here the issue really is that you don't know how to start. So you sort of, unless you have some speed, you don't know where your position is, right? So
is it same as a 0 crossing? Like whenever this back EMF was crossed,
that's right.
0.
That's right. That's right. It's very similar to, but it is same as zero crossing. Same as zero crossing. You're trying to estimate where your zero crossing is. Now, you can always fire the motor. You can always fire the motor, and if it turns, you're able to get some information from it. Right. Now let's see. That's one scheme. I think there is. You can in the see when you, that's one way of running a BLDC motor where you are actually injecting the trapezoidal currents or square wave currents. You can also run the BLDC motors with field oriented control. Okay. You can also run BLDC motors where you are using same principles as you're using in induction motor drives, and then you can begin to have speed observers, just like you have in induction motor drives, right? You can implement a whole slew. I mean, that's a whole different topic we didn't cover, but BLDC motors, or you can call them BLAC motors, which are sinusoidal distribution. You can begin to use field-oriented control principles, and then you can begin to use the same principle as we have seen here. That you can begin to estimate your speed and your so that's another way you can actually take a BLDC motor, convert it into assume it's a BLAC motor. You will have some torque ripple, but you can run it. Right. So those are the two things I can add. Maybe somebody else want to add to this sensorless control on BLDC motors.
Here also back EMF profile will be like trapezoidal, will be like the way yesterday we see the back EMF profile.
Yes, yes. Yeah, if you have a trapezoidal back EMF, then yes, you will have trapezoidal.
BLDC with sensorless are very less applications. It's very cost-effective solution.
Yeah.
Maybe PLDCs look like a cost-effective, whereas PLC is a costly, which can compete with ion induction pulsations.
Cost saving is only for the sensor bit, or other than
BLDC overall is a lot cost-sensitive application.
no, only the elimination is that only the sensors. The 3 sensors are required. So we are reducing the cost of 3 sensors or anything else.
Controller also, right? The direct control is there. Here we are implementing it.
Yeah, savings are not much. I mean, it doesn't really make sense at, well, it does make sense if you're making millions of, for example, if I'm in a washing machine business, right, and I'm making millions of washing machines, and if I can save $1 or 50 cents, then it's a $500,000 of savings to me. If I have a, so for somebody like, Maytag or something, some of the companies in the U.S. who are making washing machines in millions, then it can make a lot of sense. Then they have, most of those drives have gone into BLDC, and most of those drives, I believe, have gone to sensorless, where they're not user critical, right? If the machine vibrates a little bit, nobody's going to come and check, well, the machine is vibrating, right? It is, and by the time you notice it, it's already a bit down, so that they're very, very competitive drives, highly optimized competitive drives. But it's hard to make an argument unless you're a big company. Let's say if I'm only producing a few thousand, then it doesn't make sense, at least on a piece of paper when you're doing analysis comparison, to go sensorless.
Can we say that it is a scalar control, BLDC controller?
Right.
It is
Yes, scalar. Again, I think it's the same principle. What you apply to induction motor can be applied to DLDC as well, right? And it's very similar concept, and equations become slightly different, but you're able to apply it and use it. Anything else we want to add to this discussion? And I think TI has got some great great tools for sensorless control using for BLDC. You know, they have got some great, and they have also got some great software available on their website for field-oriented control of both induction motor drives and BLAC drives. Okay, so and their DSPs, you know, are a whole lot better suited because they have been actually one of the better better fit with respect to application is the DSPs from TI.
I have one more question. Regarding this control source inverter and voltage source inverter, is there any costing differentiation or how the application varies?
See, I think the current source inverters become so when you have a induction motor drive, right? Then we begin to differentiate between voltage source inverters and current source inverters. Okay. Now, when it comes to a permanent magnet motor, right? I don't have to worry about. I can run the motor in open in a voltage mode, right? But there is no feedback. But when I'm actually controlling currents, right? Then I have a current feedback, right? You could say that that's a sort of a current source inverter, right? But in induction motor drives, it's a different, because there you actually are just like we saw, we are actually giving voltage command, right? And in the and there you'll be giving current commands. The algorithm is different. The algorithm, especially induction motor drives, right? And yeah, I think that I'll stop there. I'll stop there.
In the case of current source inverter, you always expect to have the load.
And that's another good point you have, is you got to have a load because you have an inductor at the input, and you can't really leave that inductor open. So, and that inductor is your additional cost compared to the voltage source inverter, right? And the weight. But normally, I think you have to have a pretty big drive when you're using that. All right, let's see if we can go to part 5 of our presentation. So this is some of the fundamental stuff we're going to review here, and then we have got some 7 or 8 demonstrations which we will show you. Now, what we're going to show you is, here we're going to talk about small signal modeling, right? Small signal modeling of DC-DC converters. And I want to give you a taste of it by a simple component we have developed. And see how you can simulate these DC-DC converters by using this component. So we will we have what we have is a buck converter, boost converter, buck boost, chook, and then we have also got 2 flybacks and 2 forward converters. I'll show you, okay, in the demonstration. Now here is the buck converter, and we're going to come back to this slide in a minute or so. But let's start with the buck converter. So buck converter, essentially, we have in its simple form, you have so in the simple form, essentially that's your buck converter. Okay. You have input voltage, you have a switch, a diode, an inductor, capacitor, and this is the output. And I'm going to pay some attention to this guy here, this element here. We call this switching element. I'm going to talk about that also. So this is the buck converter, right? Now, so you switch this at a very high frequency, and that switching is averaged by this inductor, and then you have a V output, which is a function of the duty cycle at which this switch is turned on and off. Okay. So if you look at now, here are a couple of equations which are pretty straightforward. On-time event. So now here we're talking about the inductor current. Okay, on-time event. So this refers to the current which is flowing in this element, inductor, right? So you say, okay, what is my element here? Now normally here the assumption is that the inductor current is continuous, and it has got valley and peak. Okay? So inductor current has this sort of a triangular waveform, and you have got a valley and a peak. That's an assumption here in this equation. So when you calculate I peak, now I peak happens when this switch is closed. So when this switch is closed, right, the first equation applies, because when this switch is closed, the voltage here is V input. So the voltage across the inductor is V in minus V out. And if you look at the current in the inductor during that time, so let's say if this switch is turned on for a period of T on, okay, then the rise of the current in this inductor is given by this equation. I peak is equal to I valley plus V in minus V out divided by L T on. Now, this particular V in minus V out by L times T on is nothing but del V divided by L times, let's see here, times del T. Is this right? See, voltage is equal to L del I by del T. Yeah, that is correct. Okay. So essentially, that's what you're exploiting here. V across the inductor is a function of del I, del T, and L. Okay, so consequently, you have I peak is equal to I valley plus V in minus V out over L times T on. Right, that's a turn on event. Turn off event, you are here at I peak. So when you turn this off, this diode is conducting. Okay. You turn this off, this inductor current has to be continuous, so this diode is conducting, right? So, what is the voltage across the inductor at that point of time? When this diode is conducting, the voltage at this point is 0, right? If you assume diode has got -1, or you can say -1, right? So -1 volt, and then you've got a V out, right? Assuming it's a perfect diode, your I valley is given by this equation. Okay? That's the buck converter. Now, when you now if you add these two equations together, because the voltage across an inductor in a period has to be 0, right? That is the law of nature. You can't do anything about it, right? The voltage across an inductor in a period has to come to 0, right? That's the basic law of nature. Just like you have the Newton's laws, here you have this particular law. What is the name for this law? Pardon me?
Volt seconds.
Volts, yeah, but what's it's a
Volt second.
yeah, but what's the
It's just the periodicity.
pardon me?
It's just the periodicity.
Periodicity. Okay. All right. So yeah, that is so you have voltage across the inductor. Average voltage across the inductor comes to 0. So what we have done is added those two events. So D now is defined as D is T on by TSW. Okay. So we can rewrite, this is the on event, this is the off event. We add the two together, say equal to 0, because the voltage across the inductor has to be 0, right? And let's see if we can look at it. This is the, we'll come to this.